Alex going
He said he's going right.
No. It's half. Next week's the last. It's just he liked it, but he liked it so much, he just made fun of me all the time. You should play it with parents.
Good morning, guys. We're going to work through 5.4 notes. And we're going to start off with some properties. And then we'll move into derivatives. But I want us to just do this today and tomorrow. So we're going to go through just the first page of notes. We're going to see a lot of chapter 2 material kind of reappear. Product, quotient, chain, implicit, but all within the context of these new rules that we're going to learn. And so tomorrow, I just want us to just kind of get some more practice under our belt. So no new material tomorrow, but today I want to introduce each type of problem to you to begin with. So I'm going to do my work on a separate sheet of paper, just so that it's easier for you to read, since the print is kind of small here, but basically just working through this worksheet here. So these last few days, we've been learning about natural log. We learned about what the graph of natural log looks like. We learned about properties to expand. We learned about the derivative rule. And today, we're talking about the inverse function of natural log, which is exponential function e to the x. So if your natural log graph looks like this, your e to the x is going to look like this. So these are inverse functions, and today we're talking about the properties and the derivatives involved with e to the x. But first, we're going to explore the fact that they are inverses of each other, and the fact that we can use the inverse function to help us solve certain types of equations. And some nice properties that are available is the fact that if I put e to the x into the natural log function, they're going to find a way to cancel each other out, which is nice. Allows us to solve for variables that are otherwise are stuck inside a function. Likewise, if I have a natural log function, I can I can put it as part of an exponential base e, and that will also cancel out. So something in the form of e to the natural log of x, base e and natural log, they're inverses of each other. They're going to find a way to cancel out. So basically, whatever is inside the parentheses of natural log is going to be the only thing that remains, whether it's x or it's x squared minus 1 or whatever is inside the natural log. So that's nice to know that we can kind of use the inverse of one function to kind of help clean up the function itself. So we're going to explore how we can pair these properties to help types of equations. So let's look at example 1. We're going to solve, so no derivatives yet, we're just working on properties here, solving certain equations. The first example is 7 is equal to e to the x plus 1. Now, we were trying to solve for x, but x is stuck as an exponent. And normally, exponent variables are just harder to work with. It's hard to divide, it's hard to move it. But we do know that we can find a way to bring it down if it's part of a natural log expression. So anytime I'm trying to solve for a variable and it's stuck as an exponent, my thinking is always, okay, what if I make it a natural log problem, then I can bring that exponent down. So that's what I'm going to do. We're going to take the natural log of both sides so that we can have an easier time with that exponent variable, because that's ultimately what we're trying to get to. Okay. I'm going to put the x plus 1 in its own set of parentheses. Okay, so now which property can we take advantage of on the right side? Yeah, good. That exponent, that x plus 1 can come down cleanly in front. And now once we do that, we just have more options available in what we can do with it. And x plus 1 comes down. A lot easier to work with this x plus 1 now, or to work with that x. What do you know about natural log of e? Just becomes 1, right? Order pair, natural log of e is 1. So that's nice. That just goes away, or it becomes 1. Okay, so now we have a clear path to our answer. Subtract 1 from both sides. All right, questions there? Okay, number 2. We're also solving for x, but x is located in a different location here. So number 1, x is stuck as an exponent with base e, so that's where we involve natural log to undo that base e. Here, though, our x is stuck inside the natural log. So what if we involve base e to take away that natural log? So that's what we're going to do. We're going to, something to point out is that this we can't expand. We can't make this natural log of 2x minus natural log of 3. Okay, the natural log, the 2x minus 3 is inside the natural log. We can't distribute something that's inside. So keep in mind we can't do this. Okay, if it's natural log of 2 terms added or subtracted, it stays in that form. We can't expand. Okay, so it's stuck in this form. However, I want to try to get that 2x minus 3 out from under that natural log. So I'm going to raise both sides base e, trying to make it look like this. So the nice thing here is that first of all, I'm balancing both sides of the equation. Whatever I'm doing to one side, I'm also balancing on the other. And the e to the natural log, we can just make it go away, and the only thing that's left over is what's inside the parentheses. Same thing here. E to the ln of x, I think of that x as anything inside the parentheses. Anything inside the parentheses is the only thing that's going to remain. So that's going to allow us to get to that 2x minus 3. No need to worry about a natural log getting in the way. Now we have a nice clean equation to solve. Right? Add 3, divide by 2, and we can get x by itself. Divide both sides by 2. All right, any questions with solving equations, either variable stuck as the exponent or variable stuck inside the natural log? Okay, we'll spend a little bit of time tomorrow kind of practicing these problems as well. Okay. All right, moving on to some other properties here. We have some exponent properties. If I'm multiplying two bases together, that's the same thing as writing the base once and adding the exponents. If I divide bases by one another, that's the same thing as writing the base once and subtracting the exponents. And also a reminder, e is a number, right? So if there's no variable involved, e is not a variable. So if it's e squared, the derivative is not 2e, or if my equation is e to the fourth, my derivative is not 4e cubed. That's just a number, so that number is always going to go to 0. Or derivative-wise, it will go to 0. All right, so here's today's derivative rule for exponential function e to the x. The rule says if I have something in the form of e to the u, where u is an exponent expression, then my derivative is just the exact expression itself times the exponent's derivative. So that's a nice thing and convenient thing about exponential function base e, is that the derivative is just itself. But if there's anything in the exponent other than an x, we need to involve its derivative as well. All right, so we're basically going to be using these two rules a lot. Natural log of u is u prime over u, and the derivative for e to the u is just e to the u times u prime. Original function times exponent's derivative. So let's start off. Let me just do some easier derivative rules, and then we can move on to ones that are more involved. So I'm going to call this 2b and 2c before we jump into example 3. So let's say I had an equation of e to the x, and I asked for the derivative. All we're going to do is we're just going to follow whatever the rule says. So what do you think is going to be the first part of my derivative? Yeah, no changes, right? Make an exact copy. Times exponent's derivative. What's x's derivative? 1. So just that 1 doesn't really have any impact, right? So just e to the x. So the basic function, the derivative is going to be the exact same. Now, obviously, if there's more involvement with the exponent, then it's not just going to be 1, right? It's going to be something else. So, any questions so far? Okay, let's do one that's a little bit more involved, and then we can look at 3.
So would this rule also work with like regular numbers like 5, 6, 7?
Oh, you mean base 5?
Yeah.
Okay, so this rule is only for base E. We are going to be talking about other bases like base 2, base 3, base 5. It's going to be based off of this rule, but there's a little bit more complexity to it. So we're kind of doing like the parent derivative first, and then the next section, Friday, we'll learn about other bases. But this is kind of building on top of this rule. But yeah, but for today, the rule is only going to apply for base E. Yeah, base E. Same thing with logs. Right now, we're doing natural log, which is base E. But we're also going to learn about derivative rules for log base 2, log base 3, log base 5. But they all can kind of be clumped together into something that is built off of this rule. So if I have the form of y is equal to 2e to the 5x minus 3 to the fourth plus 6, same rule. So let's see if we can build a derivative. What do you think y prime is going to be initially? With the 2, right? The 2 is going to stay. Okay. So no changes, right? We're going to keep everything we see. Oops, plus 6. All right, times, I got my e to the u showing up. Now I got to do my u prime. So I turn my attention to the exponent, and I'm going to put the derivative in this space here. What's my derivative?
5 minus 4x.
And the 6 goes away, right? All right, so let me label what we just did. This is my e to the u. And then this is my u prime. Just following the rule and interpreting whatever it's asking for us to find. No need to clean up. We'll leave it in that form. Okay, make sense? Okay. So we're going to keep building on top of what we've done. So we're adding to the complexity here, each problem. All right, here's number 3. Here's our function. Y is equal to natural log of 2x minus e to the negative 2x. And we're going to find y prime. All right, so we have 2 rules. Well, there's also power rule, but the 2 big rules that we see natural log, we see e to the u. Again, we can't expand this, right? This is not, we can't distribute that natural log through. It's stuck in that form. So we got to make some decisions here. Which rule do we apply first? Right? Obviously, we see 2 rules involved, but which one do we do first? The natural log or the e to the u? Okay, why natural log? Right, so we always take, if we're deciding between 2 rules, see which one has a larger impact. Whichever affects a larger portion of the problem is going to be the first one you do. And then once we get that started, then we can work down to the smaller portion, the individual parts. Good, so I'm looking at this rule. I'm going to match everything up. Okay, what's my u value? Everything inside the parentheses, right? Everything inside the parentheses. So let's review the rule for natural log. Natural log of u says the derivative is u prime. So u prime means I'm going to take the derivative of everything I see inside the parentheses, and it's going to go in the space above in the numerator. Divided by the original u value. Whatever I see inside the parentheses, I'm going to make an exact copy and put it in the denominator. So let me label that. This is my u value. Okay, y prime equals. So u prime, we're going to take the derivative of everything inside. These are 2 separate terms, so we got to do 2 separate derivative rules. All right, what's 2x turn into? 2. Okay, we have that down. E to the negative 2x. So now we can activate our rule for e to the u. So what's our derivative for this portion here?
E to the negative 2x times negative 2.
Good. The original function times the exponent's derivative. So all this represents u prime because u prime says take the derivative of whatever you see inside the parentheses and put it in this space. Divided by, yeah, just whatever we see here, right? Just copy that down. All right, we can do a little bit of cleanup. I'm not going to worry about the negative exponent. Any questions so far? Okay, so I'm going to just do a little bit of cleanup here. combine those two negatives. Okay, any questions? Okay. If you have any questions, be sure to ask. We're just going to kind of add more and more things to our derivative process. So we're kind of speeding through all of chapter 2, just getting all the topics that we've seen. So we see a little bit of chain rule, we see a little bit of power rule, we see combinations of different rules here. Okay, good with 3? Let's look at 4. Okay, we want to find y prime. All right, we have a couple of things going on here. Can you guys list out some things that we have to involve?
Chain rule.
Chain rule, okay. Yeah, that parentheses with exponents, we definitely have to chain rule there. All right, what else? Okay, we definitely have to apply the rule for e to the u, right?
Oh,
There's,
product.
yeah, that's a big one I want us to see. Okay, so which one do we use first, product or chain rule? Okay, product is impacting the whole problem, right? The chain rule is just within that e, so that's a smaller portion. We want to do the larger portion first. All right, let me label. I think sometimes that's the hard part, just recognizing the need for product rule. I don't think we did as much product rule. I think there was a way in chapter 2 to kind of avoid product rule, because really we're dealing with a polynomial, so a lot of times we can kind of just expand and merge them together and then rely on power rule. But now we have all these different, we're going to see a lot more, these different families of functions, and there's no way to combine them together, so they have to stay separated. And so a lot of it is going to require product rule, probably more than what we've had to do in the past. So that's also why we're going to see a lot more product rule, I feel. All right, so let me label here f prime times g plus f, leave some room for g prime here. Okay, f prime. G, no changes. Copy everything I see there. Back to F. No changes. All right, G prime. Okay, let's build this piece by piece. What comes first? U. Copy everything you see, right? No changes. Okay, let me spell out what we have so far. We have the e to the u, which is part of our derivative. But now we also need a u prime, right? And u prime is this entire exponent, and this is where we have to involve what? Chain rule, right? So there's a chain rule part here. So that means there's an outside portion, there's an inside portion. Outside is my parentheses cubed. Inside is the x squared plus 2x plus 3. We'll take that whole derivative, and that's going to go in this space here. Okay. What's outside's derivative? Yeah, 3 parentheses squared. Good. And then we just duplicate what we see on the inside, no changes. times the inside derivative. What's inside derivative? That's going to go in this space here. Okay, I'm not going to ask you to clean up. You can leave it in this mess. But there's our derivative. Okay, questions? All right, example 5. Okay, so example 5, we're doing a little bit more involvement than just derivative. It's asking to find the tangent line equation. So let me highlight the big ideas behind, or the major steps involved for tangent line equation. First, we need to find the derivative. Second, we need to find the slope using the derivative. And then we can do our point slope form after that. That's our equation. All right, so now let's dig into the details here. Find y prime, so I want to find the derivative, but what's involved here? Okay, so we recognize that, right? Obviously, there's a rule for e to the u, there's a rule for natural log, but there's also product rule. We need to see that. Good. So let me label what we have here. There's my f, there's my g. Okay, let's take this piece by piece. All right, what's f prime? Good, times -1, right? We got to take care of that exponent's derivative, and that's going to go next to r e to the u. Okay, g function, no changes. F function, no changes. Okay, back to g prime, 1 over x, good. All right, look at what we've gathered here. Any questions here? Now, I would say let's not worry about cleanup, because the problem is not really asking for the derivative, right? It's only asking for the tangent line equation. So even though it's unsimplified, we can go ahead and find the slope, right? And then just merge whatever numeric value we get at the end. So how can I find slope using my derivative? Okay, and what does it need? What do I plug in? Do I have an x value that I can use? Is there an x value that's given to us in the problem? Okay, good. Yeah. So in this case, we don't have to use 0, right? There's no y in the derivative. Maybe down the line, we may see some y's in the derivative, but here it's a function, so a function is only going to require the x value. We don't need the y value. So we'll just go ahead and replace every x we see with 1 and see if that will get us cleaned up to a numeric value. That numeric value is going to be our slope. All right, I know this looks messy, but this is going to clean up nicely here. What do you know about natural log of 1? Yeah, it's just the x-intercept, right? Natural log 1 is 0. So that's nice. That's going to take out this whole thing here. So I'm just left with e to the negative 1, and how can I represent e to the negative 1 without a negative exponent? 1 over e, right? 1 over e. There we go. There's our slope. Okay, so let's summarize what information we have. We have our order pair. We have our slope. And now we do point slope. And you can leave your answer in point slope form. In fact, I encourage you guys to do that. Maybe some of you are used to slope intercept form, but point slope form is good enough. So we'll leave it in that form. Okay, any questions? We're adding more elements to it right now. Instead of just finding a derivative, I'm asking for the tangent line equation. So just continuing kind of building our problem into more and more steps. All right, does anybody still need to look at number 5? No. All right, let's look at number 6. We're finding back to finding derivative. All right, there's 2 big things I notice here. Can you guys identify some things, some process we have to involve here? Say it again? Okay, no natural log. Okay. What else? Do you see product rule there? No. There's one big thing. Yeah, it's not a function anymore, right? A function has just y by itself on the left side and everything else isolated in terms of x on the other side. So we see multiple y's. We see y's kind of incorporated into the equation. So what's that method called? When you have multiple y's and we want to find the derivative. Okay, implicit, right? So implicit says that when we come across y's derivative, we need to attach dy dx, right? We don't do anything special with the x's, but we do need to keep track of the y's. Okay, so here's my setup. Okay, let's build this from scratch here. F prime. G function, no changes. F function, no changes. Now, G prime. What's the derivative of e to the y? Oops, wrong page here. Good. E to the y times y prime, and we call y prime dy dx, right? Just to make it more detailed, more expressive. Okay, let me pause for a moment. Are we okay with jumping to this conclusion? E to the y turns into e to the y times dy dx. We're just applying this rule. And we're also involving the fact that y has its own special derivative process. It's going to have its own dy dx. Okay. Why do we not have dy dx here?
Not taking the
Good.
derivative.
Right. Only derivative. Only when they ask for derivative do we have to involve dy dx. We don't just apply dy dx whenever we see y's. Okay. All right. So let's finish the rest of the derivative. Minus. Right. Even though the y disappears, we are asking for y to begin with derivative-wise, so dy dx is going to pop up. 0 will stay 0, but careful, right? If it's other constants, it also goes 0. If we see 5, goes 0. If we see 12, it goes 0. I want to point out something else. This is kind of just something I like to do just to make sure I have everything in place. A quick check. I count how many instances of y's I see in my original problem, and that's exactly how many dy dx's will pop up in my next step. So I have 2 y's, I should see 2 dy dx's, and that's exactly what I have. So that's just a quick check to make sure that we didn't lose track of a dy dx, or we didn't include an additional dy dx that we shouldn't have, right? Just a quick check there. All right, so the calculus step is done. Now we're just trying to solve for dy dx. Any questions up to this point? All right, so I'm going to move some terms around. I want to leave these 2 terms on the left side so I can factor dy dx out. Divide the parentheses. Okay, any questions? Okay, so I want to just remind us of the big picture here. Our derivative is just, as we introduce more things, it's going to look messier, and there's more things involved. But I don't want us to lose track of the big picture. The big picture is that the concept is still simple. All this, as messy as your derivative can get, all it's doing is describing the slope of the original function. So if I give it an ordered pair, in this case, I need both an x and y, but if I give it an ordered pair, it'll give me a number, and that number is going to correlate to whatever steepness is on the original graph. So as messy as our derivative gets, our concept is still the same. We're just kind of revisiting the same concept, just with additional functions, additional derivative rules to involve, but the concept hasn't changed. Okay, any questions with 6? Okay, let's do one more problem. Number 7. Okay, so this one, I'm going to set it up. We'll talk about it, and then give you guys a chance to work on this, and I want to just be able to see how you guys do. So this one, we're going to find our tangent line equation. So it's kind of like a combination of the previous problems here. All right. What do you notice before we start the problem? Just look at it. What's involved? Okay, so also implicit. Good. Product rule. How many times though? Yeah, we gotta do it twice. Product rule twice. Okay, so I'm gonna set it up. See how far you guys can get. Now, let's do this real quick here. How many y's do you see? 2. That means the next line, however messy your derivative looks, there should only be 2 dy dx's that pop up. All right, so see how far you guys can get from here. Two sets of product rule. I've labeled them. See if you can fill in those blanks. What happens to the one on the right side of the equation? It becomes 0. Okay, let's check your second line. That's the hard part, right? Getting to that second line is the derivative portion. The rest of it is just cleanup. Okay, f prime times g plus f g prime. So g prime, the rule for e to the u is e to the u times u prime, and u prime for y is dy dx. Moving on to the product rule for my second term. Y becomes 1 dy dx. times g plus f g prime. The rule for e to the x is e to the x times 1. Okay, any questions up to this point? So look at how many y's we have, right? We have 2 y's. The second line, we should only have 2. Quick way to double check that you're not adding or taking away UIDXs that should be there. So we're going to solve for dydx. Once we solve for dydx, we can take our ordered pair, use that to find the slope. Once we have our slope, point slope form, cancel any equation. Here's my derivative equation before I find my slope. So as messy as your derivative equation looks, all this is doing is trying to create some formula to describe the pattern of your steepness of your curve. But because of the complexity, we need to involve both the 0 and 1. So 0 plugs in for x, 1 plugs in for y. Clean all that up, see if you can get it down to numeric value, and that numeric value will tell us what the slope at that point. Okay, so 0 plugs in for x, 1 plugs in for y. Remember, anything raised to 0 power is not 0, right? Anything raised to 0 power is 1. So 1 is going to stay. There's a 1 in the denominator. I'm left with negative e minus 1 over 1. Any 1 in the denominator, just make that go away to make it negative e minus 1. This is, could be, we can make it a decimal value, but we want to leave it as the exact value. So there's our slope. We have the order pair, 0, 1, and then finally point slope form. Any questions? So tomorrow, I just want us to practice with these types of problems. Under today's link, there's also this worksheet. So I'm just going to pick out problems from the worksheet tomorrow just to practice solving equations, finding derivatives. So let's just get more practice under our belt. Nothing new tomorrow. Okay. But if you can bring this tomorrow, that'll be good. All right. If you're on Teams, have a great day. See you guys tomorrow.